Whether you're an experienced user with MTWorks 2's visual programming environment or a first-time user, it's always helpful to understand how these virtual components align with the actual machine. Here you'll see that the rotary knife servo represents the cam output module. The master encoder provides input to the servo axis, translating its information through the electronic clutch in differential gear. Lastly, the photo eye mark sensor on the machine provides information to correct the position of the servo. This takes place through the virtual auxiliary servo motor. An important part of the setup for the rotary knife application is establishing the correct electronic gear ratio for one-to-one follow with the encoder. This guarantees that the rotary knife blade doesn't damage the material, so it provides a clean cut every time. The product length setting provides information to the servo so it can consistently cut the material at the right distances. The rotary cutter servo resolution and diameter define the amount of pulses per inch for comparison with the encoder's values, PE and DE. Lastly, the cut area angle is defined as a window of distance for synchronized travel with the encoder. To provide compensation during non-cut regions, it's necessary to calculate how much distance and speed should be commanded into the system by the virtual auxiliary servo motor. A picture of the auxiliary virtual motor is shown as V1 in the drawing here. This axis is used to provide the compensation via a virtual servo move, which requires a target position and speed command. These values are programmed as indirect addresses that change depending on the line speed of the conveyor. To determine these speeds, a series of calculations is required. In the first calculation, the time required for the compensation to take place is calculated as the compensation area divided by the belt speed. The second step is used to determine the amount of pulses required for the travel distance and is comprised of user-defined variables. Step 3 combines the time and distance calculations to create the compensation speed. In the end, the compensation amount and speed results are used to control the virtual servo motor. For machines configured to cut automatically without a mark sensor in place for correction, the motion controller's limit output data function is configured. This data is set according to the cut area and compensation area settings. Here, you'll see 8 bits defined for a machine with 4 blades. The limit output data is used for machine types with 1, 2, or 4 knives. Programming with registration provides a huge advantage to adjust the accuracy of each cut, which ultimately guarantees a higher quality end product through preventing the negative side effect of position displacement through unexpected stretching or binding of the material, for example. The math provided compares the difference between marks with the actual product length and then uses the error amount to provide adjustment. Here, the actual length is subtracted from the measured distance between marks, and ideally, this error amount should be 0. An alternative method is to capture the position of the servo motor relative to the position of each mark from the encoder, and then compare that difference repeatedly. If the difference fluctuates, the auxiliary virtual servo motor is commanded to correct the servo's position. An HMI operator interface connected to the MR-MQ100 motion controller provides easy control for the rotary knife application. A GT12 series terminal is used in this application with screens for operating the machine, setting parameters, and for monitoring the performance. Here you'll see a jog operation function, which allows you to jog the rotary axis in the forward or reverse direction to determine the home position. Tweaking the rotary cutter's diameter setting affects how accurately the knife will follow the encoder and needs to be programmed very accurately. On the monitor screen, the product count is displayed, along with several other pertinent machine values. In summary, the rotary knife solution from Mitsubishi Electric provides an easy-to-understand, flexible representation of the system through visual programming with MTWorks 2. This reduces the development time up to 30% and provides an advantage for machine builders who would like to tweak a virtual version of their system quickly and easily. High-speed mark registration provides on-the-fly corrections to keep the rotary knife axis on track at all times. This directly results in higher quality production with less machine downtime. Finally, Ethernet communication provides a fast open network that machine builders are familiar with and can rely on. Standard cabling reduces machine cost and simplifies the setup to other devices. Alternative solutions from Mitsubishi Electric include all of the other motion controllers that can process encoder feedback for encoder following. These include the Q170 MCPU standalone motion controller for control of up to 16 servo axes. This controller comes in handy for converting solutions, where a material gets passed through several stations before entering the rotary knife station. A Q172D or Q173D motion controller could also be used for larger machine types to control 8 or 32 axes of servo. For additional digital and analog I/O control, the MRJ3D01 I/O card can be attached to the servo amplifier. Additionally, a VFD, such as the D700, could be used to control the conveyor. For further information on the Mitsubishi Electric solution for rotary knife machines, material can be found in 5 separate components: a double-page quick reference guide, a detailed application note, complete programming files, images and movies, and this presentation. All of this material is available on the MEAU website at www.meau.com. Just click on the Industry Solutions link to find your way to the material. And that brings me to the end of this Application Solutions webinar. I would like to thank you for taking the time to listen to this presentation.